All right. Welcome to this second to last lecture in our advanced quantum course. So the topic today will depart somewhat from what we've been doing so far, because now we're not talking many electrons in atoms and so on. Now we're going to talk about individual electrons in semiconductor nanostructures. And then, of course, there's sometimes, at least the quantum dots, they're sometimes called artificial atoms, because you can make structures that behave very much like atoms, but of course they're artificial because they are man-made, but you can tune their properties by choosing different compositions and different sizes, different shapes, and so on. So that gives you a lot of freedom and has a lot of applications. So the whole field basically took off with the invention of gallium arsenide heterostructures. And to see why, I mean, you can look at a structure like this, which is ideally what you want. So you want what's called a heterostructure, so that means you have different layers of different materials, but you want to keep the crystalline quality there, and that of course requires that the lattice constants of the different materials here are compatible. They're not going to match 100%, but the mismatch, the lattice mismatch, cannot be too great, because then you cannot grow these nice structures. And if you look at a chart like this, you can see why gallium arsenide is such a nice material. So this is a plot of band gap as a function of lattice constant. And the very important thing here is that gallium arsenide and aluminum arsenide have basically the same lattice constant. And gallium arsenide has a small band gap, around 1.4. Aluminum arsenide has a much greater band gap, above 2. And you can actually tune gradually by replacing gallium by aluminum. So you can tune continuously along this line, and you can see the formula up there for the band gap as a function of composition x there. So x is between 0 and 1, 0 meaning gallium and 1 meaning aluminum. And you can tune all the way there, and you can still retain this lattice match. So that is extremely important. And you can see that there are not very many other candidates that allow you to do this. One very favorable one looked at a lot at the moment, of course, is gallium nitride, where you can replace gallium by aluminum again, and you can go towards aluminum nitride. But you can see that in that case the lattice mismatch is much greater, and there's a lot of problems there. This is the reason why it took so long before we had the blue laser, and that's basically what Nakamura got the Nobel Prize for, is for solving that problem there. So that kind of material composition there allows you to grow these very, very high quality systems. And of course it's not just restricted to quantum wells. These are quantum wells, I'll get back to that in a moment. But you can have lower dimensional structures, so these are examples of nanowires. So you can have freestanding nanowires, these one-dimensional structures, but again you can have embedded nanowires embedded in another material. They can have extremely high quality again, and obviously you can go all the way to zero-dimensional structures. So there's an example here of a very nicely looking quantum dot. So that's a case where you have confinement in all 3 directions. So that's a huge field. It plays a huge big role in tons of technology, semiconductor electronics, solar cells, light sources, light emitting diodes. All light emitting diodes are basically based on this, all semiconductor lasers. So that's what we're going to talk about today. How all of this comes about and what the properties are. So let me just tilt the camera a little bit here. We're going to talk about how this kind of heterostructure and different combinations of different materials allow you to confine electrons, much like you have electrons confined in atoms or molecules, but also since it's a structure that you control, and you can tune the composition, you can choose the dimensions, so that allows you to tune the properties, and this is what allows you to make lasers emitting at different wavelengths and all that stuff. So as you saw before, if I take a material like aluminum, gallium, arsenide, then I can tune the band gap. So it basically goes something like this, with x between 1 and 0. It starts at around 1.4, so this is the gap in EVs. So for pure gallium arsenide, it's about 1.4, and then it ends up maybe around something like this. Typically what you do is you go here to around 0.3, which gives you a band gap which is something like 1.8. So this means that now you have this aluminum X, gallium 1 minus X arsenide material here with a relatively large gap, so something like 1.8. And then you can grow gallium arsenide next to it. So let's put that here with a much smaller gap. And then, so it's got to look something like this, but it's not necessarily that the valence band moves up and the conduction band moves down. This kind of alignment is called type 1. You could imagine, of course, that they both move down, so this would move down a lot, and then this would, so you would have like a downward step for both of them. That, of course, is type 2, which is not as useful. This is extremely useful because it actually means that if you grow another aluminum containing layer over here, so this is another piece of material with a larger gap, then you have confinement for both electrons and holes. Electrons would prefer to be in here, in the conduction band, and actually holes would also prefer to be here, right? A hole, of course, is a missing electron, so the preferred place to put a hole is here, right? Because when you remove an electron, you remove the electron with the highest energy, so that's obviously going to be here. So holes are stuck here, electrons are stuck in there. So you can find both electrons and holes into this gallium arsenide, and then these adjacent layers there are barriers. And you see that if we look at the total mismatch, the difference in band gaps here, it's almost 0.4, it's something like 0.38 EVs, and then that's just like a heuristic rule which tells you that if we talk about the conduction band offset, that is something like 65% of the total band gap difference, right? So the remaining 35% is going to be down here. So that's just an observation. Of course, you can try and compute why this is, but that's what's observed. That most of the shift here, the difference in band gap, occurs up here, somewhat less down here. So there's quite a big barrier for electrons to overcome. And then, so that's how you create this confinement. There's another, in fact, quite important difference between this and regular atoms, which is the fact that electrons in gallium arsenide move as if they were a lot lighter than actual electrons. So their effective mass is way less than 1. It's something like this. So they move as if they are only 6% of their actual weight, which also has a lot of importance. One very important measure of the quality of a structure or the usefulness is what's called the mobility, which is how easily a carrier will move if you push it by an electric field, for instance. So if you have this kind of very light carrier, it tends to move much more freely. So gallium arsenide has very, very high mobility. It has one of the highest in the world if you grow it with high quality. So this is how you grow what's called a quantum well, obviously. So it's a well because you have this confinement here, and the phrase or the term quantum well is usually reserved to this kind of layered structure. So you can talk about the dimensionality, which is basically the number of dimensions that are not confined. I mean, it's a number of dimensions where electrons move freely. If you're fancy, you can say that they have translational invariance. And this is, of course, the directions in which you have a well-defined k vector. So the electron states in those directions will be just plane waves, just free electron states. So if you have what we would call a three-dimensional structure, that's just bulk. A two-dimensional structure would be something like this. Actually, you should imagine that these are just layers and they extend infinitely in all directions. So that's a quantum well. A one-dimensional structure, of course, is a quantum wire. And a zero-dimensional is a quantum dot. So that's the sort of typically spherical or similar structure where the electron motion is restricted, confined in all three directions. So in this case, there are no k-vector components left. So the first thing we might do is talk a little bit about the density of states in these different cases here. And what you can say in general, of course, is that there's a that maybe we should write it like this. There's a dispersion for the energy, which is some constant, and then there's the free electron-like behavior. So maybe I'll just write it like this, with the effective mass. And this k, of course, is a d-dimensional vector. Right? So in 3D here, I have a k, which is actually kx, y, and z. In my quantum well, my k vector just has two components, and here, in this case, it's actually just one-dimensional, and so on. So the energy here is split between the energy from the confined directions and then this free electron-like behavior from all the translationally invariant dimensions. So the density of states is, well, it's a factor of 2 from spin, and we compute per volume, and then it's a matter of summing over all the k states. So now I'm just looking at the contribution from a single confined state, but I'm summing over all k states. So what I sum here is a delta function here. Every time I hit one of my energy eigenvalues, I get in this delta contribution to the density of states. So let me plug in what you've got up there. And we can do some general stuff. You might remember that if you take a constant outside a delta function, you can take it out, but it appears upside down, if you like. So this is going to give me this constant if I take that out. So again, I give myself k, and then my delta. Like this. And all of this stuff here, I'll just call k, let me just call it k0. And if let me start by looking at the 3D case. So if I convert into an integral, replacing here, then my density of states here. So I get 2 divided by these 8 pi cubed, and then this factor. And then I get this integral delta k0 squared minus k squared integrated over k. Then I can do something, again, rather general. You see here that this factor in here, of course, I can write as k0 minus k times k0 plus k. K itself here is the magnitude of the k vector, so it's obviously not negative. So this factor there is not going to give me any contribution from the integral. It's only this factor that might be 0, but whenever this is 0, obviously this is just going to be 2k0. So I can actually treat this factor as another constant that I'll just be able to take outside. So in this case I get 1 over 4 pi cubed, and taking 2k0 out I get an e over k0 and h bar squared, and then the integral delta k0 minus k d3k. And now of course I can very easily do this integral. Because I get 4 pi from the angular integration, and then so here I get a k squared right from the volume element. So when I integrate here with the delta function, that is simply going to give me a k0 squared. Right? So the important point here, apart from all these constants, is that this is just proportional to k0. Let me just do a few more cases before we look at what this really implies. But that is the important thing, that it varies as this k0 quantity. If we do the 2D analogy, everything is more or less the same, except that now my k vector is 2-dimensional, so instead here I get 1 over 2 pi squared, right? So 8 pi cubed is replaced by 4 pi squared, and I get an e over h bar squared k0. Then I have my integral k0 minus k, but in this case there's just a single k dk, right? Because it's a 2-dimensional integration. So you see that doing the integral here, I get a single factor of k0. So this becomes e 2 pi squared h bar squared and nothing more. So that's just a constant. If you like, you can say that this is k0 to the power 0. Because then you might imagine what happens in 1D. In this case, we get, again, maybe turning here. So I have now just 1 over pi m over h bar squared k0. And then in that case, I would have an integral here from this, and we just do delta itself, and that of course is just going to give me this integral is going to give me 1. So all of this is going to be proportional to 1 over k0, or k0 to the 1's first. And finally, we can just do the 0D then case. There's not much to do here because there are actually no integrals. So it's just, well, it's basically just going back to this. It's just a sum of delta functions, if you like. So now we have there's no k, but we should still sum over all the confined states, and then it's a delta. Like this. So these densities of states here, they behave in rather different ways. And there's an important thing to remember here, because now, for instance, in the 3D case, I just said, okay, this is going to give me a factor of k0. That is obviously only true if my k0 here is actually a positive number, right? So that is the assumption when we do this kind of rewriting here, that this is actually a positive number. So it's everything I did up here was under the assumption that E is higher than En, right? If that's not the case, then of course everything inside this parenthesis here is going to be negative, and I will never get any contributions anyway. So it's a prerequisite that E is, that the energy I'm talking about is higher than the lowest possible energy, which is of course just En.
But that thing, isn't that k0 squared?
Yeah, sure. Oh yeah, sorry, yeah. That is k0 squared, yeah, sure. So it's the idea is that k0 squared, thank you. K0 squared is positive, right? That is the assumption. So yeah, well spotted, thank you. So, if we look at the 3D, I can plot them all in the same plot here. I have my En, which is the quantization energy, and then in 3D, my density of states grows as this k0, and k0 itself will just be the square root of E minus En. So the three-dimensional density of states will grow as the square root. This is the 3D case. And if there's just one band, then that's all there is. Then the 2D case is a constant. But again, obviously, only as far as k0 is actually or k0 squared is actually positive. So the 2D case, maybe I can, just to indicate confinement here, maybe I can start it here. So that it's a step function here. It goes like this. So this is maybe the first. Let's call that E1. And then when I hit the next quantized level, I get another step, and then it goes like this. So my two-dimensional density of states is it's like a staircase. All the steps here have the same height given by the effective mass. Every time I hit a new confined state, then I get another step. So another way, of course, to look at this is to say that if you look at the band structure in 2D, it's all just a bunch of parabolas like this. So this one starts at E1, and this one starts at E2, and so on. And if I'm looking at an energy up here, then of course I get contributions to the density of states from both here and here, right, from both bands. But of course my energy must be higher than E2 to have any contribution from this band. So that's why I get that kind of step there. Let's do the remaining ones here. So if I look at a one-dimensional structure with a number of confined states, I get this 1 over k0, so that's 1 divided by that square root. So every time I hit a level, I get a 1 divided by a square root, and it goes down here, I get another one, it goes like this, and another one, and so on. And basically when I just hit one of these levels here, my density of states is infinite. But it's going to be this series of inverse square roots. So this is the 1D case. And then finally, in the same plot, I can add the 0D case, which is again just the sum of delta functions. So in the 0D case, we just get these peaks here. Nothing in between. Either you hit a level and then there's an infinite density of states, or you're in between levels and the density of states is 0. So you can sort of see how things gradually move when you go from 3D to 0D. You start from this smooth square root in 3D, nothing here, and then it just increases in this smooth fashion. Then in 2D you get this staircase, and of course if you make your quantum world wider and wider, these energy levels will move closer, so you'll start getting, I can indicate that here. So if you have your 3D density of states, something like this, and if you have a very wide quantum well, you'll see that it starts looking like this. Right? So you get a density of states that becomes closer and closer to the 3D case, obviously. And then if you move to 1D, you get these divergences there when you hit a level. But of course there are states in between, as long as you're above the lowest level here. So you do find density, finite density at all energies. And then finally there's the 0D case, which is just the sum of delta functions. So it becomes more and more spiky, if you like. All right. So what we're going to do now is look at how we actually compute these levels in the quantum world case. I'm going to give you the theory, and then if you like you can implement it on a computer during the exercises. It's not a problem that you can actually solve analytically, but it's quite easy to solve on a computer. So the problem we're going to look at is the confinement of electrons in this discontinuous conduction band. So we look at this quantum well formed by the step in the conduction band. So this means that we have this barrier here, which I'll call V0, and numerically it turns out that it's about this many EV, about 0.24. So if I take my z-axis to be perpendicular to the well, then I have a potential here which goes like this. So it's a square well. I choose my 0 point here so that the potential is 0 inside the well, and then obviously it's V0 outside. And the thickness of my well is going to be d, so this is d over 2, and this is minus d over 2. And since this is a symmetric potential, my eigenstates are going to have definite parity. They're either going to be even or odd functions. So an even function, such as the ground state, is going to look something like this. That's what the ground state looks like. The first excited state is an odd function, which would look something like this. So this is the first excited, that's what I call 2 before, and this is 1. The way we're going to solve it is to look at the Schrödinger equation in these different regions here and here, and then we're going to match at the boundaries, which means matching the wave function itself and its first derivative. That provides sufficient equations to solve that problem, or at least set up the equations, and then you can solve them on a computer. So our problem says that, well, first of all, let me just let me write it in 3D. Everything, of course, is really 3D. So my full problem looks like this. So this is my three-dimensional wave function, depending on both x, y, and z. But now we know that we have these two translationally invariant directions, so this means that my actual wave function is going to be some z-dependent part, and then just a plane wave for the remaining part. So kx, x, and the y. Y, so in this case, my k squared is just x squared plus y squared. Then there's some normalization, which we're not going to bother too much about. So if I plug that in here and let this guy operate, then from the x and y components, obviously I get precisely kx squared and ky squared, which is k squared. So if I write this enk as my en plus this free electron part, right? So I can put that here. Then this factor is precisely when the Laplacian here acts on the free electron part of the wave function. So those will obviously cancel, and then I'm just left with this as an eigenvalue for the set-dependent part of that wave equation. I get a minus here, set derivative, still set-dependent potential, and then my phi set equals this En times phi of set. So this is the one-dimensional Schrödinger equation that I get for the quantized motion there. But of course there is this part, obviously, and it does give a contribution to the image. So as I already said, these eigenstates are going to be either even or odd functions. And if we start by looking at what goes on inside this central region here, inside the well, so this is a region where the potential is actually 0. So we just have inside here, we just have minus h bar squared over 2me. Second derivative, let me just write that as phi double prime equals En times phi. So clearly the solutions here are sine and cosine. And since this is a positive number, right, and if I'm looking at an even solution, an even state, then maybe I need to switch up the autofocus. What this means is that the wave function inside the well, so first set less than d over 2, is going to be this cosine. Where obviously if I plot that in here, you see that the eigenvalue is going to be h bar squared kn squared over 2me. So again, it's a form that is exactly like a free electron behavior, because this is a place of no potential energy, right? So it should be the same, but obviously not every k is going to be allowed here. So it has the same form, mathematical form as a free electron, but k is now quantized. That's what it's going to look like inside the well. Out here, the equation looks as follows. Maybe again I'll write it like this, phi double prime. But now I have the potential V0 here. So I have a V0 minus my En on phi is going to be 0. And I'm going to look at the bound states. So my En is somewhere here, which means that this is now a positive number for the bound states. Right, so now I'm looking at a different case. Up here, in this case, I wanted a function with a property that when I differentiate it twice, I got a negative number, right? Because I have a minus here and this is positive. Now it's the reverse, because this is negative and this is positive. So now I want a function such that the second derivative is also positive, right? Otherwise this won't be possible. And that function obviously is the regular exponential. So let me write that in a slightly funny way. I'll write it as a and a cosine kn d over 2. That's obviously just a constant. And then here I'll write it as a Qn, and then Z minus D over 2. What I've done here is I've added a bunch of constants. This is obviously constant. Also, e to the q d over 2 is also constant. And of course, the reason I did this is that now this function is automatically continuous. Right? If I put z equal to d over 2 or minus d over 2, those two will match. So I already took care of continuity in this way. And obviously also if you plug in here, what you'll see is that another way of writing the energy is gonna be this. So replacing the cosine by an exponential means that I invert the sign here, so I get the minus, but I also have a V0 from the potential energy. But of course this energy is the same as this energy, which means that there is a connection here between K and Q. So the final thing I have to do is look at continuity of the derivative. So I'll look at phi prime. So I have this common factor of A that I might take out. Cosine differentiated is minus sine. And the other one gives me a minus Qn in front. And then again the cosine d over 2 and all of this again. Right, so in this case the derivative just amounts to multiplying by minus Qn. Here cosine becomes minus sine. Then what do I do now? Any suggestions for continuing here? Well, what I need to make sure is that this derivative is continuous. So I should put z equal to d over 2, and if I do this I get my a times, actually a cancels, so I get a minus, which also cancels, and then sine kn d over 2, and if I do that down here I get my Qn cosine Kn d over 2. By the way, here, if I were a little more careful, actually here, I mean it's plus minus, but minus is for the right hand side, plus is for the left hand side. We're just going to look at what happens at z equals to d over 2, and obviously you get this. And you can see that very nicely the A factor cancels, obviously. So I'm left with this condition. So that's one equation among two unknowns, K and Q. But I have another one, which is what I get by equating these two here. So you might add that also here. So h bar squared k squared over 2m is the same as v0 minus this thing here. So that's another equation among the same two unknowns. So two equations, two unknowns. That's got to be possible, right? Solving it. In practice, you might find it easier to actually just use the energy as the unknown. So expressing, right? So this is just the energy, this thing here. So you can express both K and Q as a function of energy, and then you can also plug that in here, which means that if you look at something like, you could call this an f function as a function of energy, which is just the difference between those two, so kn sine k e over 2 minus q cosine. If you look at this and you express everything in terms of the energy, obviously this difference also becomes a function of the energy alone. And what you can simply do is vary the energy between 0 and V0, which is obviously the range in which we're going to find solutions. And then you just plot this f function. And it'll turn out to be something like this. And every time you have a crossing here, that's a valid solution. So that is very easy. It's you just step through this interval in 10,000 or 100,000 steps and find each root, and that gives you the valid solutions. And you can, of course, you can try and be fancy. You can go in more coarse steps, and then you can do fine stepping if you want to zero in on the solution more accurately. It's not a great idea to try something like Newton-Raphson, because that is very sensitive to where you start. And if you start here, obviously you're going to get this solution, but you have to pick all possible starting points to make sure that you get all the roots, which is not trivial. So it's a better idea simply stepping through the possible range of solutions and then just looking at zero crossings. So that is the task for you, and you can obtain the energies there, and if you like, you can also plot the wave functions. There are expressions in the lecture notes for this A constant here that gives you normalization. And let me finally, before we have a short break, let me just briefly tell you what we get if you have the odd solution. They're very, very similar. So in this case you have, of course, a sine. And here you have, again, a plus or minus depending on whether you are to the right or to the left. A sine k d over 2, same exponential, right? It's the same solution we're solving, same equation we're solving. So you get something like this, and you can easily see that now if I take the derivative, then this is going to give me a cosine, and this remains the same. So the quantization condition I get here is now that k times cosine k d over 2 has got to be minus q sine. So if you compare this to this, right, you interchange sine and cosine, and then you get an extra minus here, because when you differentiate sine, you just get cosine, not minus cosine. Here you got rid of the signs because cosine differentiated gave you minus sine. So this is the condition for the odd states. So you might call this the even f function, and you can define a perfectly analogous function for the odd states and look at the roots of that equation as well. You will find that they are, actually what I did here is not right. The lowest solution is always going to be an even one, and then you get an odd solution, and an even and an odd. They always alternate like this, and the lowest one is always an even function. This is completely general for these symmetric one-dimensional potentials. Okay, so the plan now is to look at one-dimensional and a little bit at two-dimensional structures. So obviously there are very simple cases, which is having these square potentials in more than one direction, as we already had there. So if you can have square confinement in many directions, and especially if you're in the limit where the barrier is infinite, that gives you a very, very simple model. So it's just like you have these standing waves in a number of directions. So we're not going to talk a lot about that. That's kind of obvious, right? If you have like a cube quantum dot, it's just like a standing wave in 3 directions. Everything is quantized. What we will do instead for quantum wires is to look at a more elaborate case, which is also closer to reality, and that is that of an infinite cylinder. This is going to be my Z direction. There's a radial parameter here, and obviously there's also some angle with respect to an arbitrary direction. So that was this is supposed to be the center here. The radius of this wire will be r. And just to make things simple, we'll use what is called the infinite barrier approximation or infinite barrier model, which is obviously just that the potential is much, much greater outside the wire than inside the wire. This is not a very good model for this gallium arsenide heterostructure that you saw before, because the actual step is some fraction of an electron volt, but it is a good model for a freestanding structure. So it's a structure in vacuum. Right? The barrier for jumping from the structure into the vacuum is quite large. It's something like 4 or 5 eV, which is close to infinite for an electron. So for a freestanding wire in vacuum, this is a decent model. So what we're going to do here is obviously work in cylindrical coordinates. So let me remind you that the Laplacian in cylindrical coordinates has a radial part, which is this. Then it has an angular part. And then it has the regular set dependence, because we don't do anything about that part. It's only the 2 perpendicular coordinates, x and y, that we express in this polar manner here. And again, we're looking at, actually, you could say h bar squared over 2me Nabla squared on your wave function equals simply the energy, Enk, times the wave function. So I simply omitted the potential energy. So this is obviously with the understanding that when you hit the boundary here, the wave function should vanish. That's a role played by this infinite barrier. It forces the wave function to vanish identically on the perimeter periphery there. So that's understood. That's the quantization condition. So maybe now I could, again, if I multiply through here, I could say that I could have this kn, which kn squared, which is 2me over h bar squared times the quantized part of the energy. Again, remind you that total energy is this. So I could do that, and I could say that the wave function itself, since this is a separable equation, should be on a product form. So we know that there's going to be a free electron part for the motion along the wire for the z direction. The 2 other variables, r and theta here, are separable in this manner. So it means that my wave function will be some function of r times a function of the angle theta, but since nothing actually depends on angle here, this is just going to be my regular exponential here, where m is an integer. If m is an integer, then this is a periodic function, so when I go a full turn here, this function will be back to its original value, right? So the angle, this is actually the angular momentum for the z direction, which is obviously quantized. So if I do that, well then operating here will just give me a minus k squared, which will give me precisely this part of the energy. Operating here with this guy here will give me a minus m squared. So if I put all that together, let me try and do that. So I might multiply through here by this constant here. So I get d2 dr squared plus 1 over r d dr minus my m squared over r squared. All of this on the radial part. Right, that's what I get from this and this and this. And then from this part I get precisely this, but that's cancelled by the identical term on the right hand side. So I've got this, and then I multiply through by this, so all of this is actually gonna be minus this kn squared times my r function. With, of course, the extra condition here that if I put this r equal to the radius of the wire, then this function is going to vanish. I don't know if you are familiar with that equation, if you recall seeing it. We have discussed it, at least some of us, in another course. Yeah,
Bessel's equation.
it's a Bessel's equation. That's right. So it's basically the equivalent of a plane wave in cylindrical coordinates, right? Of a free particle, but now written in cylindrical coordinates. And of course, it is in a sense, it's a free particle because the potential energy is zero. So if we didn't have that confinement condition there, that would just be a free particle. So that's right. The solutions are Bessel functions. It's a second order equation. There's going to be two linearly independent solutions. One is the J Bessel function, or the regular Bessel function. The other one is the Y Bessel function. But the Y functions are not regular at the origin, so we cannot use those. Right? The Y functions have divergences here at the center, so they're not allowed. So in the end, my R function actually becomes the mth. There's some normalization which I won't bother writing, but it's the mth Bessel function times this k here, which I might actually write as kmn. It's fun. It will depend on m as well, times r. That is that's the regular solution to that equation. Again, I have another mathematical solution where this is the Bessel Y function, but I cannot use it because it's not regular. And of course, the requirement now that the function vanishes at the perimeter means that kmn times capital R should be one of the roots of the Bessel functions. I call those lambda. These are Bessel function roots. So let me try and illustrate briefly here. So I have the different Bessel functions. The first, zeroth Bessel function corresponding to an angular momentum of 0 looks something like this. So it's like a decaying, oscillating function. The amplitude here decays as the square root of x asymptotically. But you see that there are some roots. So this is what I mean by lambda 0, 1. It's the first root of the 0th Bessel function. So this is, of course, this is 0, 2, and this is 0, 3, and so on. So every time that Bessel function crosses the line, I have a possible solution. So that white curve there, that was for the Bessel 0. If I put m equal to 1, I get a very similar curve. I mean, it's not just the displacement, but they look quite similar. So this is my J1, Bessel 1 function, which obviously also has infinitely many roots. Here's lambda 1, 1, and here's lambda 1, 2, and lambda 1, 3, and so on. And then I could go even higher angular momentum. This is the J2 and so on. These Bessel functions, so Jm of x goes as x to the m for very small arguments. Right? So J0 is a constant, J1 starts off linearly, J2 starts quadratically, and so on. So that of course means something for the wave functions as well, right? So if you ask about the probability to finding an electron in the center of the wire, it's only m equals 0 that's going to give you any contribution there. They are the only ones with an amplitude in the center. So if you remember, this looks very much like what we've seen in other atomic cases, like the hydrogen atom. Higher angular momentum means that the probability of being close to the center becomes less. It's this centrifugal potential. Anyway, every time you have a root here, you get a valid solution. So for instance, the ground state is what you get here. This is the first root. So this means that I have my k, the corresponding k, which is just the Bessel root divided by radius, and the associated energy then is h bar squared like this, and the wave function is just this Bessel 0 with this argument lambda like this, right? So that's a function, as you might imagine, that simply goes like, yeah, I can draw that. It goes something like this. This is R. So this is the lowest radial function of the quantum wire. Most likely place for the electron is in the center, and then the wave function goes down like this, vanishes at the perimeter. So that's the case for the one-dimensional quantum wire. And again, it's if you had a different kind of confinement, you find something which is qualitatively quite similar. A lot of quantized levels, and the lowest ones are the ones with some probability to be in the center of the wire. And now let's finish off with the 0D case. So we'll look at a spherical nanoparticle, something like this. Again, with a radius capital R, some axis here, and if I have a certain position, I have an R and two polar angles, theta and phi. And again, I'll say that my potential here has this simple form: 0 inside, infinite outside. And my wave equation is like this. Well, let me write it as E in L. What can I say about this structure? The mathematical structure of the wave function. Because this obviously looks very much like an atom, right? It's a spherically symmetric 3D case. Kasper?
Is the function separable into angular and radial parts?
That's exactly right. And what are the angular parts, remember?
Oh god.
I guess you'll actually write this, that will make it easier to remember. The wave function dependent too.
No.
Okay. But you're right, there's a radial part, so it's separable. Will depend on those two quantum numbers. And then the angular part, which you ought to know, all of you, is the spherical harmonic. Right? As always, that's always the case in any spherically symmetric 3D problem, that the angular part of the wave function is a spherical harmonic. And then there's the radial part. And the nice thing here is that Laplacian in 3D has a radial part, and then it has an angular part, which we usually just write like this. So everything that has to do with differentiation with respect to angles is hidden in this L squared operator, which is really the square of the angular momentum, which has a very complicated expression that you don't need to remember, because the important thing is that L squared on a spherical harmonic gives you L times L plus 1. That is the essential property of the angular momentum there, that the spherical harmonics are the eigenfunctions and the eigenvalues are these simple functions here. And in case you forgot, L is a non-negative integer. M is the projection. So that means that I get this very simple equation. Okay, let's spell it out. Minus r squared over 2e, 1 over r, d2, r squared r, and then minus L plus 1 over r squared. Everything on r gives me E in L times r. So since this is an eigenfunction of everything here, I can just cancel it on both sides. So I'm left with this radial equation here. So you see that this is just the kinetic energy, right? Radial and angular kinetic energy. There's no potential because the potential inside the sphere is 0. So this is again with the understanding that this vanishes. Right? So the potential is simply via the boundary condition. And now you might see that this equation here starts to look quite similar to the Bessel equation. The Bessel equation that we had before, well, there are slight differences. There's this different radial operator in the cylindrical case, and then instead of L times L plus 1, we just had m squared. So there's this extra 1 here. Otherwise, the structure is the same. And again, we can, I can introduce a wave number, KNL, which is again square root 2me NL over h bar squared. So if I do all that, I get 1 over r d2 dr squared r minus L plus 1 R squared, everything on R, is then my, it's minus KNL squared times R. There you are. So this is a very similar equation to what we had before, and the solutions are also very similar. Again, you can think of this as the spherical analogy of a free particle. Right? It's still a free particle because it's moving in a place with no potential energy. The confinement is solely via this boundary condition. So a plane wave or a free particle in spherical coordinates is not a Bessel function, but it's something very similar called a spherical Bessel function, which we write as with a lowercase j. So that there are this quantum number L here determines what spherical Bessel function I'm talking about. And again, there are some roots for this function. I can write this in this way, but to have a valid solution, I need this to vanish on the edge of the sphere. But the spherical Bessel functions behave very similarly to the regular Bessel functions. So this could be my J0 of x. It has a first solution here, which is then something I could call beta 0, 1, which is actually just pi. You can very easily see that in the case where L is 0, if L is 0, then I have something which is pretty simple. I have this operator on my function equals a negative constant times the function itself. This is not, of course, my standard one-dimensional kinetic energy, but if I can fit that in here, if I do my usual trick of defining a p function, which is just r times my r function, right? So I have r times r, so that's my p function. Then I have this extra 1 over r, which I'll multiply onto the other side. So if I do that, and let's just look at the L equals 0 case, then I am left with something that looks exactly like my zero-dimensional, or my usual one-dimensional case. Right? So obviously p in this case is sine. Could be a sine. I cannot use the cosine. There's also a cosine solution that I cannot use. Why is that? Anyone spot that? Again, very similar to the hydrogen case.
Because cosine of 0 is 1.
Yes, and why is that not allowed?
Because it has to vanish at the center of P.
Brilliant, brilliant. That's exactly right, because r is going to be finite and multiplied by lowercase r. So my boundary condition for the p function is that it must vanish at 0, which means that the cosine is not allowed. So only sine functions are allowed. So this, of course, means that so this is my p 0 in. What did I write it? Okay. In 0. So my r function here is just the sine over r, which of course is regular. This is regular at the origin, right? Because sine x over x just goes to 1. And obviously, the boundary conditions is that k times capital R must be an integer number of pi, right? So the first 0 is just pi, and the second is 2 pi, and so on. So this function here is 0th spherical Bessel function. Well, it is in fact just sine x over x. The following spherical Bessel functions are more complicated. They're all on the form like sine times some polynomial in 1 over x plus cosine times another polynomial over x and 1 over x. But in those cases, you cannot actually find the roots analytically. You have to solve for the roots numerically. But the upshot is naturally the same, that all energies are quantized. This again is the ground state, so it's a function with a maximum in the center of the sphere, decaying like this sign here. And the energy, the ground state energy, we might finish on that. This E01 is then h bar squared, and in fact pi squared divided by 2m r squared. And so on. So these S states in these spherical nanoparticles are very simple.